This video lecture is in continuation with the previous lecture that was all about Newton's universal law of gravitation. In this video lecture, we will look at why did Newton assume the inverse square dependence. I hope you enjoyed this video, so we'll get started. In the previous lecture, we looked at Newton's universal law of gravitation. In that, we had two relations. First was the attractive force between two objects is directly proportional to product of the masses, and the force is inversely proportional to the square of the distance between them. Now in this lecture we will look at why did Newton assume that it is only inversely proportional to the square of the distance between them. Now for this we will need the concept of Kepler's third law. If you remember, according to Kepler's third law, the square of the time period is directly proportional to the cube of the mean distance between the planet and the sun. From this we derived the relation that was t square is equal to k multiplied with r cube. In that k was a constant, and if you shift this r cube on the other side, we had this relation t square upon r cube is equal to k. So this is the relation that we will use for this topic. Let's say that this equation is equation number 8. Now we will start discussing why did Newton assume this. Consider a planet which is revolving around the sun in a circular orbit. Let's say that the mass of this planet is small m and it is revolving in a circular orbit. Now see, we have already discussed in Kepler's law. According to the first law, the orbit of every planet is elliptical, but now in this case we will just consider that the orbit is circular for convenience so that we can derive the relation. So in this case I assume that the mass of the planet is small m and this planet is revolving with a constant speed, and the speed I will assume it to be v. Now the distance from the planet to the sun, I will assume that this is small r. These are the consideration that you need to make. I'll just write mass of the planet is equal to small m. Speed of the planet, I will assume it to be r, and the distance between the planet and the sun, I will take it as r. When the planet revolves around the sun, it traces out a circle, so we can say that this planet is performing circular motion. And when we talk about circular motion, we will deal with centripetal force. Now I have already explained what is centripetal force, but still I will again explain this in short. Let's say if a particle is moving along the circumference of a circle, so we say that if this is the center of the circle, we say that the particle, the direction of velocity of the particle is always tangentially outward. So what it means, the object which performs circular motion, it always tries to move in the outwards direction. But if you want this particle to perform circular motion, so what we need, at every point we need to pull this particle in the inwards, or we can say towards the center. So there's a force which acts on the particle when it performs circular motion, which acts along the radius and towards the center. This is known as centripetal force. So in this case, this planet is moving along the circumference of a circle, that is the orbit. So it will be acted upon by an attractive force which will pull this towards the center, or towards the center, which is the centripetal force. Now to find the centripetal force, we have a formula, and that formula is centripetal force is given by mv square upon r. Let's say the centripetal force is F is equal to mass into square of the speed divided by the distance. Now again the notations are same. M is the mass, V is the speed of the planet, and R is the distance. Now let's say this is equation number B. I will mark this as equation number B. Now we have a general formula. When we talk about speed, speed is given by distance upon time. Now if I represent this formula in symbolical form, so we can write speed is equal to distance upon time. Now when we talk about distance, so distance scale, now again look at this. I will consider the planet again. Let's say the initial position of the planet is at A. Now when this planet starts revolving and it completes one revolution, it will come back to its initial position. So in this case, the distance traveled by this planet will be taken as the circumference itself, and the circumference of a circle is calculated by using this formula, that is 2 pi r upon t. So the velocity of this planet will be 2 pi upon 2 pi r upon t. Now let's say this is equation number C. Now in equation number B we have this term v square. So in place of v I can replace v with this 2 pi r upon t. So the equation will be transformed. So the centripetal force will be written as F is equal to m upon r, and this v square will be replaced with this formula, that is equation number C. In place of v I will write 2 pi r upon t whole bracket square. Now we derive this equation from equation number C. For reference you can write this. Now solving this, F is equal to m upon r. Now square of this bracket will be 2 square is 4, then pi square multiplied with r square divided by t square. Now in this equation this r will cancel this r. So the formula is F is equal to m multiplied with 4 pi square r divided by t square. I hope till now everything is clear to you. Let's say this is equation number D. Now moving back to the Kepler's law, if you look at equation number A, in this we need t square upon r cube. So t square, we already have a term which is t square, but we need r cube. Now look at this equation number D. In this equation I have t square. We already have t square. Now we need r cube. So to find r cube, what we can do, we can multiply the equation by r square. So we will need some modification. In this case what we will do, we will multiply equation D, we will divide and multiply. We will divide and multiply equation D by r square. So what will happen to this equation? This equation will be m multiplied with 4 pi square r upon t square. This will be multiplied and divided by r square and r square. The equation will be m 4 pi square. This r into r square will give you r cube divided by r square multiplied with t square. In this we need some changes. थोड़ा सा हम इन terms को rearrange करके लिखेंगे. So I can say F is equal to m4 pi square upon r square multiplied with r cube upon t square. इसी फॉर्मूला में मैंने बस इन दोनों टर्म को थोड़ा सा सेपरेट लिखा है. Let's say this equation is equation number E. Now from Kepler's law we already looked at this. T square upon r cube was a constant k. Now if I write the reciprocal, अगर मैं इसका reciprocal लिख दूं, which is r cube upon t square, so this will be 1 upon k, right? So in this case, if you look at equation number D, we have this relation r cube upon t square. So r cube upon t square will be replaced with 1 upon k. So the equation will be F is equal to m into 4 pi square upon r square. Now this whole term will be replaced with 1 upon k. So the equation will be now m multiplied with m into 4 pi square upon r square into k. Now in this case, again I will modify this equation. I will write this as F is equal to m4 pi square upon r multiplied with 1 upon r square. Now there is a reason why I am writing this in this format, because in this, if you look at this, the mass of the planet is constant. This number 4 is again a constant. Pi is also constant. We know pi is equal to 3.114, and this k, इसको हमने already discuss किया था from Kepler's law. K is the constant. So in this case, this whole term is a constant. So from this I can directly say that F is inversely proportional to 1 upon r square. 1 upon r square. Now in this case, if you remember, r was taken as the distance between the planet and the sun. So from this what we can say, as Newton said, the attractive force is inversely proportional to the square of the distance. यहाँ पे सिर्फ representation को हमने change किया. We took d initially, but now we take it as r. So this is how we derive the relation. This is how we explain why did Newton assume the inverse square dependence. So ये आपको एग्जाम में आ सकता है. It may be asked to you. आपको Kepler's law पूछेगा. They will ask you to state Kepler's law, and उसके अंदर सब क्वेश्चन बनेगा. Explain why Newton assumed the inverse square law. and this is how you will explain this. And this relation itself explains how did Kepler's third law help Newton to derive this relation. I hope this is clear to you. Thank you for watching this video. We'll meet in the next lecture.